using my own PPT, but you can read these materials from the book by A.K. Ghatak in the chapter, the lasers and optical fiber. That chapter is there. Maybe it is in 27th or 28th chapter. Okay, depending upon which edition they are. So I am coming back to that, what I was doing in the previous class. Is the screen is visible? Hello?
Yes, sir.
Okay.
Yes, sir, it's visible.
Okay, so fine. You see, this is the emblem of earlier Delhi College of Engineering. Okay. This emblem. Have you seen this emblem?
Not yet, sir.
No, in my screen it is coming. So, because this university was earlier known as Delhi College of Engineering, so at that time this was the emblem. So this I have made it for some other people much earlier, how to understand optical fiber, but everything is not part of your syllabus. Some select portion. This I have explained. The optical fiber has application in optical communication. Okay, both analog, digital, in all types of communication. In the previous class, just I am showing you so that you can recall. In optical communication, like you see, whatever the digit was as the information, here that is not coming in the order. Same. So there is some error is there. Okay, so in optical communication, what we want, if we send 10 to the power 9 digits, 10 to the power 9 digits from here to there, so we require that the error should not be more than 1 digit. So that is why we call that as a bit error rate in optical communication is 10 to the power minus 9. That is, if you are sending 10 to the power 9 bits, only one error is coming. Okay, so very less error is required. Okay, so in optic communication, we always express that. Why optical fibers I have used? Because there is a more bandwidth, low loss, of the optical signal within the optical fiber compared to the electrical signal within the copper cable. Okay, it has a low loss, so that reduces the cost per connections. So this I have explained. This also. Can anyone tell me that what is the material we use for the making optical fiber which is used in the communication?
Doped silicone.
Yeah, dope.
FiO2, sir.
Okay. And this also I have defined. RIP, I have told you what is RIP. Okay. In graded index fiber, the maximum refractive index is at the center of the core and it decreases continuously within the core up to the value of N2 and then it is N2 in the cladding. Okay, so that is called graded index fiber. Again, this graded index fiber can also be of many types. If it is grading like this, we call parabolic graded index fiber. And if the grading is linear, like it is in this manner here, in this way, then we will be calling that as a linear graded index fiber. Okay. And the difference between N1 and N2 is very small. Why we use different profiles? To control the pulse dispersion. Okay, to control the pulse dispersion we use. And also we use graded index fiber so that whatever the changes is happening within the cladding and all, it is not affecting the core. I believe we were doing this. I have defined meridional reach. And this also has been done. What is a ray? Ray is a direction of the wave propagation. This is core cladding interface. That is, core is having N1 refractive index, cladding is N2. This is incident reach. Reflected. That is possible when incident angle is greater than the critical angle. If it is not, then we will be partially reflected, partially transmitted. Okay, if there is no absorption, then reflected plus transmitted light will be the incident light. But there is always some absorption within the material, so it is not equal. Okay, this is the angle. Now, how total, and if theta is increases, let's say increase, theta t increases. Okay, maximum it will go up to 90 degree. And corresponding to 90 degree angle of refraction, or in the transmitted side, corresponding to this angle of refraction equal to 90 degree, whatever the incident angle is there, we call theta critical angle. Okay, theta critical. More than that, then there will be no transmitted, all will be reflected. That means no energy is going into the cladding, most of them get reflected back into the core. So that we call total internal reflection. This is like that. If this angle is less than critical angle, then again the rays are going there in the cladding. Okay. If the angle of incident is greater than the critical angle, greater than the critical angle, then they will not go into the cladding. They will be here and they're reflected back. Again, within the fiber, they will be, so they are propagating along the core of the fiber. I want to derive the formula for the numerical aperture of the fiber. Okay, numerical aperture of the fiber. So you see it is like this. Can you derive this? Mr. Isank.
Yes, sir.
Have I done this derivation in the class?
Here only.
Okay.
No, sir.
Okay, so just it is like that. The light is launched here within the fiber. Okay, it can be making a smaller angle also here, but if this angle is a small, then this angle will be a small. Okay, and this angle is small, then this one will be greater because all three has to be 180 degree. So I am considering the maximum angle here, corresponding to which the angle of refraction is this. This should be as low as possible, so that this angle should be equal to or greater than the critical angle. So what is happening? This is my maximum angle. In between all the angle, like if I make here a smaller than this angle, then what will happen? This angle will be also small. So this angle will be small, means this will be greater than critical angle. Okay, so let me say that this is the limiting or maximum angle which will satisfy the condition. So if you apply here Snell's law at this interface, what will happen? The refractive index is n0, and this is sine theta 0 angle. I am calling as a max, but you can call any angle. Sine theta 0 max is the angle. So this should be equal to this side n1 sine theta, and the theta will be like that 90 minus theta ci. Am I all right?
Yes, sir.
I mean, this angle will be theta, but theta I can write 90 minus theta ci, because these two sum will be 90 degree. So sine 90 minus theta ci will be cos theta ci. Am I all right? Hello?
Yes, sir. All right.
So this, up to this. So this is the one expression. Don't go with this. I will be coming from this expression. Now what I am doing is, yeah, please put off something. The mic should be off. Okay, so what we have done is up to this point. Am I all right? Now let's see if there is an angle of refraction here. So corresponding to the limiting angle of a critical angle, if you apply here the Snell's law, then it will be n1 sine theta 1, sine theta ci is equal to n2 sine theta to this side, and that is, what is the minimum value? When this will be angle 90 degree n2 sine theta, then corresponding to that angle will be the critical angle. Okay, so I can write n1 sine theta ci is equal to n2 sine 90 degree, and 90 degree means it is 1. Therefore sine theta ci will be N2 by N1. Am I correct?
Yes, sir.
Theta, see here in the diagram it is not given here. Here if you are putting, okay, so that one will be, so sine theta Ci each equal to N2 by N1, and therefore cos theta Ci will be how much? Cos theta Ci will be 1 minus sine square theta Ci. Sine theta Ci is N2 by N1. So it will be N2 square by N1 square. And their square root. So what will be there? That one will be equal to N1 into 1 minus N1 square by N2 square by N1 square. So N1 square minus N2 square root, this N1 will be cancelled. And therefore it will become N1 square minus N2 square power half. Is it all right?
Yes, sir.
No, if it is not all right, then what I will be doing is this. Is the white screen is
Yes, sir. Visible.
okay? Okay, so what I am doing is that this is core and this is cladding. Okay, this is the fiber. Is the screen is visible?
Yes, sir.
Yes.
Okay, and this is the end. Okay, that is the fiber, it will be there. So this type of a thing. I hope it is clear to you. Now what is that? This is the axis of the fiber. Okay. Now what is happening? The light will be incident. Okay. So light will be incident means the light will be incident in this manner. You will have a pulse type of a thing and the light will be incident this. So some of the light is going like this way, okay, along the axis. And any light, I mean, you will have this light also, this light also. So I am considering this as a maximum one, light one, okay. So I am removing this. So now what is happening? If this is the incident light, this is the incident light making here. So this is that angle, maximum. They will be getting refracted here. And if this angle is greater than critical angle, so I have put what I have put here. Here it is in air, so I have put that as a N0 refractive index. And sine theta 0 max I have written. Why I have written max? Because this angle is getting reflected, all these. Beyond this angle it will not be. So that is the minimum angle here. And corresponding to that, that is the critical angle here. So this I have written as equal to N1. It will be sine this angle I want. So this angle is a theta. Okay, so and this I have in my diagram, I have put as a theta Ci. Okay, Ci. So this angle, if I write theta, so theta will be equal to 90 minus theta Ci. Okay, so I am putting 90 minus theta Ci. So that is equal to N1 cos theta Ci. Okay, and now at this point, what is happening? Here you have to apply this Snell's law. So here is you will be applying this Snell's law. So this angle will start when beyond the 90 degrees. So here if you apply there, then what will happen? N1 cos sine theta Ci would be equal to N2 sine 90 degree, because beyond that this will be there. So sine 90 degree means it will be 1, so it will be N2, and therefore sine theta Ci is equal to N1 by N2. Sine theta Ci is equal to N2 by N1. Okay, N2 by N1, and therefore cos theta Ci is equal to square root 1 minus N2 square by N1 square. Okay, and that you will be substituting it here. So N1 will be cancelled and it will become N1 square minus N1 square minus N2 square, their power square root. Is it clear? Hello? Mr. Isank,
Yes, sir. Yes, sir.
are you able to see the screen?
Yes, sir.
Okay, so this is the screen. So that is what I have done it there. Now this is equal to the numerical aperture of the fiber. That is mathematically. Again, it is an N0 is a air. If it is a water, like we can keep it in the water, then the numerical aperture will be N1 square minus N2 square divided by N0. If N0 is a water, you can write N water. So numerical aperture will be this. It will be rather reduced. Okay. So numerical aperture is basically what? It is the sine of the semi-vertical angle of the cone of the light which is launched into the fiber. And most of the light remains guided through the core. Guided through the core means they are not going into the cladding. Okay, so that light we call that property is called numerical aperture. That is sine of the semi-vertical angle of the cone. N0 is here 1. That is why we can define. Okay, mathematically this is the definition. In general, that is called the light gathering capacity of the optical fiber. Am I all right?
Yes, sir.
Okay, so that is what I am doing. So This is the one. Now, what is acceptance angle? You can say the acceptance angle is this theta 0 max. That is called the acceptance angle. From this side or that side, that is the semi-vertical angle of the comb. That itself is called the acceptance angle of the fiber. That is, if you launch the light ray, making angle less than this or maximum of this angle, which will remain guided through the fiber in the core, corresponding that angle is known as maximum angle. Okay. This I have already explained, fiber materials, in the previous class. Am I right or not?
Yes, sir.
Yes, sir.
So what is the material which is used for the optical fiber? We do use in the telecommunication grade optical fiber as a silica as a material, but silica is doped in such a manner that core is a higher refractive index and the cladding is lower refractive. Again, doped means what kind of materials we are doping? These are the typical doping material: germanium oxide, P2O5, B2O3, fluorine. And their refractive indexes changes like this. Here, this diagram, this I must have made that is a bit long. Here it will be 1.48. Okay. So that is, if you are doping germanium, its refractive index is increasing. P2O5 increasing. B2O3. This is an exact value, that is 1.458 at lambda 0, 850 nanometer. Okay, so actual value of the refractive index for a given light, we should define that its refractive index is this much at this wavelength or for this wavelength of the light. Okay, otherwise prior to this you have studied what you have studied, that it looks like a refractive index is value and for a material and it is constant for all the range of different lights. It is not. Okay, so this is rays, wavefronts and modes. So mode you do not need to study. So like what happens when the light is propagating through the optical fiber? This is again core, this is cladding. Okay, core and cladding. Okay. So the light is going, but if you measure it as a wave, it will be coming like this. That is, its amplitude will be like this, amplitude of the electric field associated with the light. If you square it, then what will happen? This will also be positive, this will also be positive, this will, so it will be coming like this. So again, I am coming back. Okay, so that is the one. So these are not a part of your one, so you do not forget. Now, we have classified optical fiber as two types. One is a step index fiber, another is graded index fiber. Okay, that is how the refractive index are distributed within the core and cladding. Optical fibers are also classified in terms of the mode, how many modes are propagating. I will be explaining you what is mode. So if only one mode is propagating, we call it as a single mode fiber. And if many modes are there, many modes means many possible rays are there, then you call as a multi-mode fiber. So like a typical example here, you see the core diameter is this much. Okay. Core diameter is this much. So this range is also possible. This is also possible. And in between will also. So many ways are there to go. So that we are calling as a multi-mode fiber. If we reduce the dimension of the core, then what will happen? Typically, very one range type of a things are going out. We will be calling that as a single mode fiber. Okay, single mode fiber. Single mode fiber has a core dimension much more smaller. compared to the cladding dimension. Okay. So fibers are classified in terms of the mode as a single mode and multi-mode fibers. Two types of the fiber. Whether a fiber will be a single mode or multi-mode, it will depend upon the refractive index of the core. Also, it does depend upon the N1 and N2, and also it depends upon the wavelength of the light which is propagating. Like for a wavelength, say for some fiber, for red color, it may be a single mode. For blue color, it may not be a single mode. That is possible. That is possible. So fibers are classified in the terms of the number of modes propagating as single mode and multi-mode. Again, another parameter which is more important for you people to study it, the relative core cladding index difference. This we have already done, numerical aperture. Okay. What is relative core cladding index difference? That is N1 square minus N2 square divided by 2N1 square. Okay. And that will be roughly equal to, proportional, not exact equal to N1 minus N2 divided by N1. Because this we can write N1 minus N2 into N1 plus N2. And the denominator also we can write that as a 2N1 squares. So N1 plus N2 we have taken each approximately equal to 2N1 and we have cancelled it. So this is coming approximately, that is there. So this term, exact definition of relative core cladding index difference is this N1 square minus N2 square divided by 2N1 square. Okay, 2N1 square. That I mean, approximately can be written N1 minus N2 divided by N1. Normally, many times this is expressed in terms of the percentage. That delta value is 1%. Delta value is 1.5% or 2%. Okay. So exact value you can find it out, but many a times people use this as an approximation. Similarly, we define another parameter called the V value of the fiber. V value depends on this expression. Okay. So lambda is the operating wavelength, that is the signal which is going into the fiber. N1 and N2 are their refractive index. This value is like this. If this value is more than 2.4048, okay, then the fibers remain the multimoded. If V value is less than 2.4048, that is called single mode. Again, that value, if we change the lambda, you can change this. That is why I have said that for red color means has a higher wavelength, this will be small. Okay. It may satisfy that 2.4048 condition, but if you reduce this to blue wavelength, then this term will be increasing. It can become more than 2.4048. Then it will become this multimoded fiber. So these are three important parameters used in the fiber, although this may not be considered as a part of your syllabus because this comes from the how light is moving within the fiber, taking it as a wave, not as a ray. Okay. So later on, in a higher level, we teach the wave model of the light wave propagation through the optical fiber. So from there we infer that single mode, multi-mode classification also comes from the wave analysis of the light which is propagating through the fiber. But for your you should know all these three parameters, important parameters. A is the core radius of the fiber. Okay, these you do not read. This is not for yourself. No, they are not for year. Okay, so let me go to the is the whiteboard is same?
Yes, sir. Visible.
Okay. So now I am doing something called the time dispersion. That is a part of your syllabus. In the optical fiber. Okay, so what is that? So that is like this. I think I should have used the same diagram, previous one. This must be available here. Okay, this is the one. So now what will happen? One will be along the axis, light range. So that is going like this. And from here I am measuring the distance. So any light wave which we have launched like this, okay, so some portion will going along the axis. So along the axis L of L length of the optical fiber, how much time they will be taking to travel? L length. L divided by C by N1. Am I all right? That is the time they will take. Is it all right?
Yes, sir.
Hello? That is the time that is they will be taking. But any range which is going like this, and then this, okay, let's say that this is the L length. So that will take more time. Am I all right? Because your whole information is based on these pulse, okay? But in pulse, what is happening? The middle portion is taking this much time, and any other range than that, they will be going like this. So suppose if I incident another range, sorry, this one, okay? So what this angle is less, so that another angle will be further less. So that one will be like this, isn't it? They will be going in this manner. But this is the maximum time taken, that is from here. Okay, this one. Maximum time taken. For traveling the L length will be how much? So that I will be calculating. That is the T minimum. Okay, and then I will be calculating T maximum. Okay, T maximum I will be calculating. So can anyone calculate what will be the T maximum? Okay.
L/C होगा.
How much?
L/C होगा क्योंकि अगर AR लेंगे तो एक होगा उसका N यानी कि उसका different index.
No, but the distance traveled is a difference. This is the least distance. Okay, distance traveled, because they will be traveling in a zigzag manner. So that distance will be different. Okay, that distance will be different. And then that you will be dividing by this. Okay, so if we calculate, so this will be taking more time. Okay, so that you will be calculating how much is the T max minus T minimum per unit distance. Okay, that will be coming an expression like this, that is T maximum minus T minimum will be proportional to the distance between N1 minus N2. I have not derived the exact expression, I will be deriving. Okay, but let me tell you that will be coming T max minus T minimum. That will be proportional to N1 minus N2. Okay, that is the difference. In communication, what we want, that this should be as low as possible. Okay, it should not increase more. Again, there are two ways to make it. If you reduce the core dimension, okay, reduce the core dimension, then this zigzag path will be reduced. Another way is that if you reduce the core dimension. Okay, other way is that if it is proportional formula wise this, so if we reduce these two, we can't make it as a N2 equal to N1, then there will be no total internal reflection. Okay, no total internal reflection. So we cannot make, so there should be a slight difference should be there, but the difference should not be high, because if the difference is high, then this value will be high. That means the meaning is that whatever you have spoken and out of which one light pulse is generated, that is on that pulse there is a information. So what will happen? The part of the information which is going along the axis, they will be reaching earlier, and the one which is going from this side, they will be reaching later. And if they are reaching later, that means complete information we will not be able to retrieve. And therefore we want this should be as low as possible. This is called pulse dispersion, this phenomenon. Okay, pulse dispersion. But we are considering more of a time. So we are calling time dispersion also. The time dispersion of the pulse. Okay, so the time dispersion of the pulse is this. It is given in the book. So I give you an exercise to you people to derive a formula for this. Okay, what is the formula? It is given in the book. Okay, let me tell you what is the formula. What is the formula? Must be here. Is the screen is visible?
Yes, sir. White screen.
But I'm not interested in white screen. I am referring the book.
Okay, sir.
Lasers from here. So these I have already covered, total internal reflection and all. Okay. Optical fiber also I have covered this. This I have defined the as a relative core cladding index difference. And this I have also told that approximately you can write like this. Am I all right? Hello? So
Yes, sir.
this I have done it. And this is the way it is propagating. I have shown you in the movie type of a thing, working diagram, how it is happening. Okay, so core cladding air. So it is like this. This is also refractive index profile. I have given it in another manner that it is there. Why they have put it like that? This is not on a scale. Otherwise, the refractive index should have been, air is a 1. Isn't it? Is this, and N1 is around 1.45. So 0.45 we are making this much of bigger, and otherwise we are making low. So this is core cladding and the air. So actual refractive index profile, you can put it like this. Okay. So 2B is around 125 micron. 2B means it is a cladding diameter. Cladding diameter. Okay. So in this way, you can put it. You don't go with this. Why
Excuse me,
glass?
sir. Sir,
Yes.
can you leave us early because we have a class test from 11 o'clock?
Whatever is there, I will leave you before 11. Okay.
Okay.
I do not. So my point is that everything I have covered here. Yeah, pulse dispersion in multimode optical fiber. Okay, so T minimum, as I said, that L divided by C by N1. Okay, so it is N1 L by C corresponding to theta. So you T max is this. It will be coming. That they have derived it here. I want that as an exercise. You people should do it on your own. Okay, and derive an expression. That is ray dispersion in a multimode optical fiber. That is from there. So it will be coming like this, an expression, L length. If cos theta is 0 means they are propagating through the axis. Okay. And if theta is making any other angle and maximum angle, they will be making as a N2 by N1. Okay. So that minimum and maximum will be like this. Okay, expression. If you that is do this T max minus T minimum, it will be coming N1 by N2 minus 1. And that is N1 minus N2. That is why I said that pulse dispersion is proportional to the N1 minus N2. And therefore, you can find out like this how much the pulse dispersion will be there. Okay, so derive that expression, that expression, that what it will be. Okay, so this is all about that. So I have in this class, I started with the optical fiber. I derived the expression of the numerical aperture and how the light range is moving, what are the materials we are using. That portion I have done. So pulse dispersion, that is ray dispersion, is an important aspect for your numerical problems and all. So that you do it. Okay. In the next class, whatever is there, I will finish the optical fiber portion. Thank you very much. I have left you around 3 minutes.